Good morning. Here we need to start the third part of Lebesgue measure, and the topic is differentiation of monotone functions. And now the definition starts for the Vitali cover. Let tau be a collection of intervals, then we say that tau covers a set E in the sense of Vitali. If for each epsilon positive and for each x belonging to E, there is an interval I belonging to those collection of intervals such that x belongs to E and length of the interval is strictly less than epsilon. Suppose tau is a set of the collection of intervals. Let's say I1, I2 up to In, right? And it covers the set E. If for each epsilon positive and for each x belonging to E, let's say here I'm having x1 and this is x2 up to so on, right? Then there is an interval, let's say I1, belonging to this collection such that this interval I1 contains the point x1 and the length of interval I1 is strictly less than epsilon. Similarly, for the point x2, there exists an interval I2 belonging to the tau, such that length of this second interval is strictly less than epsilon. So whatever interval that belongs to this collection tau, for such an interval, the points of E are belonging to that interval, such that the length of those intervals should be strictly less than epsilon. So if we are having infinitely many points in E, then there exist infinitely many intervals containing the points of E, right? So the collection of such intervals covers a set E. Very fine. Okay. Let's move on to the Vitali covering theorem now. The Vitali's covering theorem states that the lemma 1, let E is a subset of R. R is a set of real numbers with finite measure of E, and tau be the collection of intervals which cover E in the sense of Vitali. Then given epsilon positive, there is finite disjoint collection of intervals in tau. Disjoint collection means their intersection is empty. The measure of E minus the union of these intervals. The union of all these n is starting from 1 to capital N, the natural numbers. So this measure should be strictly less than epsilon. So the collection of intervals which are covering E, we are subtracting their union from E and then taking their measure, and that measure should be strictly less than epsilon, right? Okay. Let's move on to the another definition about the set of derivatives of f at x. So the first is d plus fx. This plus at the top is about taking the limit superior, right? So we are taking here the superior limit on fx plus h minus f of x divided by h. H is tending to 0 positive, the positive values, right? Which can be further written as limit h tending to 0 positive, taking the supremum of x plus h minus fx divided by h. Very fine. Okay. Similarly, if I am having the negative sign at the top, d minus fx, we are again talking about the superior limit on f of x minus f of x minus h divided by h. Please take care of this. Here I am having fx minus f of x minus h, and h is tending to 0 positive, which can further also be written as limit h is tending to 0 positive, taking the supremum of f of x minus h divided by h. Third, when I am having positive sign at the bottom, which means we are talking about the limit inferior. H is tending to 0 positive, f of x plus h minus f of x divided by h, and this can be written as limit h tending to 0 positive, we are taking the infimum of f of x plus h minus f of x divided by h. Then if we are having the negative sign at the bottom, which means we are taking the limit inferior, h tending to 0 plus f of x minus f of x minus h divided by h, and further it can be written as limit h tending to 0 positive, and we are taking the infimum of f of x minus f of x minus h divided by h. So these are the 4 definitions for the derivative of f at x, right? Now if you notice that clearly, d plus at the top, which is having the limit on the supremum value, this will be always greater than equal to d plus at the bottom, right, which is limit on the infimum value. So can I write that? So clearly d plus at the top for fx is always greater than equal to d plus at the bottom for fx, and d minus at the top for fx is also greater than equal to d minus at the bottom for fx, right? And if all these are equal and is giving the finite limit, then we say that f is differentiable at x. So we say that f is differentiable at x, and define f dash x to be the common value of the derivative at x. So we define this to be the common value of the derivative of x, right? Next is the important remark. You can also take this as your theorem. It is very important. If f be an increasing real valued function, real valued function means the function is giving the real value in its range or in its output, right? So let f be an increasing real valued function on the interval closed interval ab, then f is differentiable almost everywhere. Then f is differentiable almost everywhere, and the derivative f dash is measurable, and the integration of f dash x dx for the limits a to b, because the interval is closed interval ab. So this integration is less than equal to f of b minus f of a. So this remark is very important. Please keep this in mind. So now in the next content we will be going to discuss the function of bounded variation, right? Okay, thank you. Stay blessed.